Hello, good evening.
Good evening, sir.
Any doubt from last class?
Sir,
Yes.
I did not get how the phase difference between y and a is pi.
Y and
A.
displace acceleration. Okay.
Yeah.
Any more doubt? Okay, from this part, you can say, whenever you have to calculate phase difference, first, convert the function in same term. Like for displacement, we have function in sine, that is in positive sine, positive a sine omega t. But in case of acceleration, we have minus of omega square a sine omega t. So first we have to convert this minus of sine omega t into some positive value. So I have just converted like this.
Okay, sir. Then the phase difference is pi. Okay.
Is it clear?
Yes, sir. I did not see the conversion part.
Okay. So whenever you have to calculate phase difference, first convert function in same type and then calculate the difference of their angle. You'll get the phase difference. So in last class, I had defined you about energy, potential energy and kinetic energy up to this part. Next, if you add these two terms to get total energy, total energy E is equals to kinetic energy plus potential energy. Kinetic energy we have half m omega square a square minus y square, and potential energy half m omega square y square. If you expand this particular part, half m omega square a square minus half m omega square y square plus half m omega square y square. This part and this part are same but in opposite sign, so they will cancel out. So you're left with just half m omega square e square. And this is equals to maximum kinetic energy or maximum potential energy, and which is constant. So we can say total energy will be constant in this SHM. Is it clear?
Yes, sir.
Now, related to this part, let me define your relation of time period and frequency for different quantity. Relation of time period and frequency first, displacement, velocity, acceleration, potential energy, total energy, kinetic energy, and then total energy. This is time period. And this is frequency. For displacement, if you have time period t and frequency f, then velocity will have same value and same for acceleration. But in case of potential energy, it oscillates with half time period as that of displacement and having twice frequency as that of displacement. Similarly, kinetic energy will be same. In case of total energy, which is constant, and for constant quantity, time period will be infinite and frequency will be 0. Gautam, is it clear?
So I did not get the last one.
Total energy is constant. It means there will be no change in its quantity at any time. It means it will take infinite time to get changed by any amount, which is not possible. Hence, time period is infinite and frequency is just reciprocal of time period, so it will be 0. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Nabila, done?
Yes, sir.
Okay. A particle of mass 2 kg performing an SHM having displacement as y equals to 0.02 sine 10 pi t. Find first time period of source, second maximum kinetic energy. Third, frequency of oscillating potential energy. Let me give you a hint how to simplify this part. First, just try to compare this expression to the main part, y equals to a times sine omega into t. You'll get the value of amplitude and omega. From omega, you'll get time period as omega equals to 2 pi by t, and then frequency equals to 1 by time period. Now apply the formula to get maximum kinetic energy and frequency of oscillating potential energy according to the above table. Try to find.
So the potential is separate question, right?
Yeah, it is the third part of the same question.
The third part is frequency of oscillating potential energy.
In first part, we have to calculate time period of actual wave. In second part, you have to calculate maximum kinetic energy, and third part, you have to calculate frequency of oscillating potential energy. Okay.
Okay.
If you solve this part, you'll get time period of source, that is time period of displacement. And similarly, this will define your frequency of displacement. Now you have to define how it is related with frequency of potential energy and oscillating kinetic energy.
So Kmax is
Maximum kinetic energy according to the formula I defined you in last class. Kmax is half omega squared ma squared. This part.
okay, sir.
So you have mass of particle, omega, and amplitude. Nabila, you got any answer?
Sir, I'm trying.
Okay. In place of pi square, you may write just 10. Pi square is roughly equals to 10. Razan, just tell me what will be the value of amplitude if you compare these two equations
0.02.
and omega.
10 pi.
Good. So from this part, we can say A equals to 0.02 meter and omega is 10 pi. Now just equate this equation to 2 pi by t, and pi will cancel out. So t will equals to 2 by 10, that is 0.2 second. So this will be time period of oscillating displacement. And frequency related to this part will be 1 by time period, that is 1 over 0.2. So it will be just 5 hertz. Try to find maximum kinetic energy. Good, Krishna. Kmax according to formula is half m omega square a square. Half mass of body is 2 kg. Omega is 10 pi. So on squaring, it will become 100 pi square. A square is 0.02 squared. So it will be 2 into 10 to the power minus 2 whole square. So 2 and 2 will cancel out. So 100. Pi square is 10. Square of 2, 4. And square of 10 to the power minus 2. It will be 10 to the power minus 4. So it will be 4 into 10 to the power plus 3 into 10 to the power minus 4 that is 4 into 10 raised to the power minus 1. So it will be further 4 into 1 by 10, that is 0.4 joule. Mazia, is it clear?
Yes.
Next, we have to define frequency of oscillating potential energy. In above part in this table, I define a relation between frequency of oscillating potential energy and frequency of displacement. If you have frequency of displacement F, then potential energy will oscillate with twice frequency as that of source. So for source, we have frequency 5 Hertz. So what will be the frequency of oscillating potential energy?
10 Hertz.
Good. So frequency of oscillating potential energy will be twice of that of source, that is 10 Hertz. Nabila, any doubt?
No, sir.
Okay. You all have written?
Yes, sir.
Next, you will be asked to plot graph related to these 3 different variations. So next is this is energy versus displacement. For potential energy, which depends upon sine square omega t and sine 0 is 0. So graph related to that part will be like this.
So this is
This
graph
is,
of what, sir?
yes,
So this is a graph of what?
potential energy variation with respect to displacement. Next is for kinetic energy, which is maximum at mean position and minimum at extreme position. So graph related to that part will be like this. This is kinetic energy, and total energy is always constant. So this will be total energy. Now this point is extreme towards right. This point extreme towards left. Next, there's point of intersection this one, this one. So if you join these 2 points, it will define you at point at which kinetic energy equals to potential energy and half of total energy. This point is a by root 2, positive side, and also towards negative side. So you'll be asked at what displacement potential energy and kinetic energy becomes equal, and what will be the value of total energy at this point. So total energy remains same. Kinetic energy and potential energy at this point will be half of total energy. And this point is a by root 2, or displacement is a by root 2. Is it clear?
So why is it a by root 2?
Let me prove this part. According to the formula, kinetic energy equals to half m omega square a square minus y square, and potential energy is simply half m omega square y square. So at this point, potential energy and kinetic energy are equal, so just equate these two terms. So half m omega square, half m omega square gets cancelled out. So you're left with a square minus y square equals to y square. Move this y square towards right. So you'll get a square equals to 2 times of y square, or simply y square equals to a square by 2. So y will be plus minus root under the entire term. So it will be a by root 2.
Okay, sir.
It means at this displacement, kinetic energy and potential energy are equal. Just draw this particular graph. Have you all done?
1 second, sir. Done, sir.
So this is all about energy in SHM, kinetic energy and potential energy and total energy. Next is calculation of time period for different SHM. Calculation of time period for different oscillation. For any motion, first try to calculate restoring force by displacing the block from its mean position. Suppose in case of spring mass system, a block is attached at this point, so this will be mean position. So if you displace this block towards left side or right side, so due to expansion or compression, a restoring force will develop into it, which will tend to move this block back to its initial position. So first, for any different motion, try to calculate restoring force. So it will be like F equals to minus of K times X, where K is called spring constant or force constant. Now, F equals to mass times acceleration minus of K times of X. So A equals to minus of K by M times X. A as velocity is displacement by time, or simply dy over dt. So acceleration is differentiation of velocity. So if you put the value of v to be dy by dt in this part, you will get second derivative of displacement with respect to time. Now put the value of a to be this and this expression. So second derivative of displacement with respect to time plus k by m times x equals to 0. So this is general expression for this particular part. Now, if you compare this to the above, which we have derived in acceleration or general equation of SHM, so you will say coefficient of displacement, and this is k by m, and that part coefficient of displacement was omega square. Just 1 minute, let me show. This was the general differential equation of SHM. So if you compare these two segments, we have coefficient of y, which is displacement in this part, is omega square. So first is double differentiation of displacement with respect to time plus omega square times y equals to 0. And from this equation, which is similar to this part, double differentiation of displacement with respect to time plus k by m times x equals to 0. So it will be y. I'm calculating in terms of y, x. So on comparing these two equations, you will get omega square equals to k by m, or k equals to m times omega square. That's why I've written the value of k in potential energy in above part as m omega square. Now we have to calculate time period for this. So just move this square to right side. So omega equals to root under k by m, and omega is nothing but 2 pi by t. So time period for this part will be root under m by k. Gautam, any doubt?
No, sir.
Now, for each different motion, first try to calculate the value of spring constant related to force experienced by that particular block by displacing it from mean position. Now, if you calculate k from this expression, put it in the formula for time period. General formula of time period will be 2 pi root under m by k. Just write it down. I'm defining with different SHM and how to calculate time period. Just write it down.
What did you tell about mean position and all?
The block at position for which there is no force acting on it is called mean position. So if it is placed along any one side towards left or towards right, due to its displacement, a force will develop into it. That is called restoring force, which will tend to bring back to its initial position. Okay.
Okay.
we all done?
Yes, sir.
Now, using this concept, first let me define you how to calculate time period of simple pendulum.
Sir.
Yes,
Sir, I also see a formula like time rate is equal to 2 pi into root y by a.
y by a, where y is
Y is the displacement and a is the acceleration.
okay. According to formula, acceleration equals to minus of omega square y. Okay. So if you move this y to other side, omega square will be equals to a by y. Okay. So omega is equals to root under a by y, and which is equals to 2 pi by t. Okay. So you may use this particular relation, but for this part, you have to calculate acceleration as well as displacement, which will be more difficult to solve. That's why we are calculating in this way. Okay.
Okay, sir. But how did we get a is equal to minus omega square y?
I defined in this particular part in last topic. Let me just show you. Just say this.
Okay, sir.
Now, next is simple pendulum. Suppose from any support, a string connected to bob is oscillating about this. So we have to calculate force acting on this bob at this instant. So due to its mass, force will act along this way due to gravity, mg. If you extend this line, so this theta and this theta will be equal, corresponding angle. So if you break its component into two parts, one of the force will be along this way and the other one along this way. Adjacent to theta will be mg times cos theta, and opposite of it will be mg times sine theta. Now, which of these two forces, mg cos theta and mg sine theta, will be responsible to restore this bob back to its initial position, that is mean position?
mg sin theta.
Good. So we can say mg sine theta is acting as restoring force. So a restoring force equals to mg sine theta. And since it is restoring in nature, so there is some negative sign attached with it. Now, for a small angle, sine theta is equals to theta. So we may write this expression as minus of mg times theta. Now, let's say length of this string is L and displacement from its mean position to this point is x. So theta equals to length of arc by radius. Now, if you substitute the value of theta as x by L in this expression, you will get minus of mg x divided by L equals to restoring force. Gautam, is it clear?
Yes, sir.
Now, the coefficient of x in this restoring force is mg divided by L. So it will act as spring constant related to this part, we can say. Is it clear?
Yes, sir.
So on comparing, we can say spring constant is equals to mg by L. So time period equals to 2 pi root under m by k, which is equals to 2 pi root under m by k, which is mg divided by l. And mn cancel out. So you're left with 2 pi root under L by G. So this will be our final expression of time period related to simple pendulum. Minashi, any doubt?
No, sir.
Okay, just write it down.
Sir,
Yes.
yes, sir. So the time period only depends upon the length.
Yes, from this part we can say length, that is distance of center of mass of bob from axis of rotation, and next is g, that is net acceleration of this particular system at this instant. I will define you more clearly this particular formula. Up to this part we can say it will depend upon length and gravity. It will be independent of mass of bob. Okay, Gautam?
Yes, sir. But if you think about it, also depends upon the mass of bob, right, and the force applied.
No. Mass and mass term gets cancelled out. So it will be independent of mass of bob.
So, but a heavier pendulum takes more time to come back, right?
It will be due to viscous force acting during its motion. If there is no viscous force in surrounding, all bob will take same time.
Okay, sir.
Have you all done?
Yes, sir.
Now in this part, time period equals to 2 pi root under L by G. So L defines you distance of center of mass of bob from axis. And G is net acceleration. So related to this part, you will be asked first, what will happen to the time period of simple pendulum if it is placed at center of Earth? if placed at center of Earth. So first tell me what will be the value of gravity or acceleration at the center of Earth?
0.
Good. So if acceleration of gravity at center is 0, so if you put in this expression, t equals to 2 pi root under L by 0, so it will become any number divided by 0 is
Infinity.
good. So time period becomes infinite. It means pendulum will behave as if it is at rest. There will be no any motion in it. Similarly, in case of free fall, net acceleration of system will be 0. So time period of pendulum will be infinite. So this type of question will be asked from this part. Are we all done? Okay, let me ask a question related to this part. Suppose in a swing, a boy is first standing at this point. And next, he sits over it. How will the time period in these two cases will be related? Let's say time period of this is T1 and time period of this is T2. Will there be any change in time period in these two situations?
So the boy's on a swing.
Yeah. So first he is standing and second he is sitting. So how the time period in these two cases will be related with one another?
So in the first one, the distance will be less. So time period.
Distance from
Axis will be less.
to
Because
which
it's
part?
from the center of mass of the person and
Good.
axis.
So in a standing position, center of mass of body will lie at this point, and in sitting position, center of mass will lie to this point. So more the distance of center of mass from axis of rotation, it will have more time period. It means T1 will be smaller as compared to T2. Is it clear to all of you?
So could you explain once more?
In first part, while standing, the center of mass of this man will lie at this point. But in second part, while sitting, center of mass moved slightly downward, so it will move to this point. So distance of center of mass from axis of rotation in first case will be from this point to this point, distance of center of mass. And in second case, it will be from this point to this point. So which is longer, in first case or second case?
Second case.
The more the distance of center of mass from axis of rotation, it will have more time period. it means T2 will be greater than T1. So you will say as distance of center of mass while sitting will be greater as compared to standing position. So T2 will be greater than T1. Raza, is it clear?
Yes, sir.
So what did you write that as distance of?
COM, short form of center of mass.
Okay, okay, sir.
Have you all done? Nabila, done?
So just the diagram is left.
Okay.
Done, sir.
Next is spring mass system. First, we have to calculate how spring constant related with length. So first is spring constant. Suppose spring having area of cross section A and length L. So K spring constant equals to Y A divided by L, where Y is elasticity, A is area of cross section, L is length of this particular spring or natural length of this particular spring. So you'll be asked, suppose a spring is divided into some segment like this.
So what is Y?
Y is elasticity, Young's modulus. Let's say the ratio of division is 1:2, 2:3. So you'll be asked, what will be the spring constant of these three different segments? So how to solve? First, for each segment, since it is given in terms of ratio, we can take first segment as x. So second segment will be 2x and third segment will be 3x. Sum of these three individual segments will be equals to actual length of a string, that is L. So x plus 2x, 3x plus 3x, 6x equals to L. So x will be equals to L by 6. Now for each different segment, for first part, length is x, second one is 2x, and third part is 3x, which is equals to L by 6. So it will become L by 3 and it will become L by 2. So K1 equals to YA divided by its length, that is L by 6. In second part, K2 equals to YA divided by L, that is L by 3. In third part, K3 equals to YA divided by length, L by 2. Now, YA by L is nothing but a spring constant K according to this relation, which is this term. So on comparing, we can say K1 will be 6 times of K, K2 will be 3 times of K, and K3 will be 2 times of K. So this is how we can solve spring constant if it is divided into different segments. First, for each segment, try to sum up to get ratio in terms of total length. Then according to the formula, you will be able to calculate a spring constant of different segment related to the main part or original spring. Krishna, is it clear?
So how did you relate at the first after like K1 is equal to 6 into YA by L? So from there,
First, just 1 minute. Since this particular spring is divided into 3 segments, having ratio 1 is to 2 is to 3. So first ratio I've taken as x, second part as 2x, and third part as 3x. Sum of these 3 individual will be equals to actual length of a spring, that is L. So first I have calculated the value of x. Then for each segment, I define its length. For first part, it will be L by 6, 2x where x is L by 6, so it will become L by 3, 3x where x is L by 6, so it will become L by 2. Then K1 will be equals to YA divided by its length, that is x, which is equals to L by 6. So L divided by 6, so 6 will move to numerator. Okay.
okay, sir, I got it.
Similarly, in this part and this part. Now, in this particular bracket, YA by L, which is nothing but equals to K. So I put the value of this to be K in this expression. That's why K1 becomes equals to 6K and so on. Gautam, any doubt?
No, sir.
Okay. I'm giving you just 5-minute break, then I will define you the combination of spring series combination, parallel combination. Okay. I'm giving just 5-minute break. Okay. Have you all done till this part?
Yes, sir.
Next is how to combine different spring and what will be key equivalent related to that combination. So first is series combination. Suppose a spring having spring constant K1, another spring constant K2, and its mean position is at this point. Length of this spring is L1. L1 and L2 are their natural length when there is no extension or compression. Now, if you stretch first spring to this part, so total length will become L1 plus X1 . Similarly, in second one, L2 plus X2. Net displacement of this particular system is from this point to this point. Now, in this series combination, the spring is massless. So for massless spring, string, row, tension at each point will be same. Similarly, in this part, since spring are massless, so force developed at each point will be same in both spring. So we can say displacement is different for different spring, but force is same for both. So we can write net displacement equals to displacement in first plus displacement in second. Now, according to the formula, F equals to minus of K times X. So X will equals to so we can write according to the formula F equals to minus of Kx. So X is equals to F by K. So it will become F by K equivalent, F by K1, and similarly F by K2. Now, if you take out F minus F as common from whole, you are left with 1 by K equivalent equals to 1 by K1 plus 1 by K2. So this is equivalent formula to find combination of spring in series. It will be valid for horizontal combination as well as vertical combination. Gautam, is it clear?
Yes, sir.
Okay, just write it down.
It's a minus because it is restoring first, right?
Yeah. According to this concept, try to find K equivalent and time period for this part. Minashi, you got any answer?
No, sir, try.
Okay. Just put the value of K1 and K2 in the above formula and you'll get K equivalent. Then time period equals to 2 pi root under m by K. You will get time period related to this part.
Sir, in terms of M,
Yeah, since mass of block is m. Gautam, you got any answer? Just see, 1 over K equivalent equals to 1 by K1. K1 is 3K and K2 is 6K. So, good result, but you have to calculate K equivalent. So just take reciprocal of your result. Good. So if you take LCM to be 6K, it will be 2 plus 1, that will be 3 times, that will be 1 by 2K. Since we have to calculate K equivalent, so just take reciprocal of it. So K equivalent will become 2K. Minashi, is it clear?
Yes, sir.
So time period equals to 2 pi root under m by K, and K we have 2K. So this will be your time period. Krishna, you have to answer time period like this expression. You don't have to further simplify it.
okay, sir.
Nabila, any doubt?
No, sir.
You all have written?
Yes, sir.
Next is parallel combination. Suppose two different spring, this one connected to block having spring constant K1 and K2. Mean position is this. Now, if you stretch or compress this particular system, this is final position. So displacement in both spring is same in this part, but due to different spring constant or different stiffness or rigidity of spring, it will have different restoring force. For this first part, it will have F1, and second part, it will have F2. So total force acting on this block will be sum of these two individual forces. So in this part, we can say displacement is same, but restoring force is different. Similarly, let me define you another example. Let's say this is first spring. Second one. Now, if you move this spring towards any one side, so this was initial position, that is mean position. Now on extending to any one side, this is fine position. So X is same for both spring, but difference is one spring is compressing down, the other one is stretching. So if you have to calculate restoring force related to this part, so in left one spring, which is compressing, restoring force will be along this way. In right part, which is extending, restoring force will be opposite of it, like this. So net restoring force in this will be sum of these two individual forces. So we can say this is the same as parallel combination we have in left part. So both combination be treated as parallel combination. Yes, Gautam?
So I did not get the blue diagram.
Okay. In this part, since block was initially at this point, so if you move this block slightly towards left, so one of the spring will get stressed and the other one get compressed. But compression and extension in both spring will be seen related to this part. Is it clear?
So there were two springs.
If you displace this particular block slightly towards left side, so this black one is getting stressed by how much? X amount. Similarly, this blue one will get compressed by how much? X amount. Is it clear?
So both of them are attached to opposite walls.
Yeah.
Okay.
So in this combination, we have same displacement for both spring, but one is compressing and the other one is stretching, but displacement in both part is same. So the restoring force in both due to both these two spring will be along same direction. So net force acting on this block will be sum of these two individual forces. So this is again parallel combination.
Sir,
So
I think I did not get the setup, the initial setup. Like, how does it start?
we have two rigid wall or support. Two springs are connected from it, and there is a block at its junction. Now, if we displace this particular block towards any one side, it will start to oscillate like this. Is it clear?
Yes, sir.
So we have to first consider by displacing it by small amount towards any one side about its displacement or force, how they are related with both spring. So in this part, we can say displacement in both spring is same. One is stretching and the other one is compressing, but both having same displacement. So we can say this is parallel combination. Is
Okay.
it clear?
Yeah, got it now.
So net force acting on the block will be sum of all individual force due to spring. F equals to minus of kx. So it will be minus of k equivalent times x, minus of k times x, and minus of k times x. X being cancelled out. So on solving, you will get k equivalent equals to k1 plus k2. So this is k equivalent for parallel combination. And parallel combination may be of two types, just like first, this, and second, this. Minashi, any doubt?
No, sir.
Okay. Using the above concept, try to find combination of these different spring, then calculate k equivalent, and then time period. Good, Gautam. Good, Krishna. This arrangement may look like this. So in left part, we have two spring which is connected in parallel. So K equivalent will be sum of these two parts. So K plus 2K will become 3K. And this is also 3K having mass 2m. Raza, now how these two spring are related? Series or parallel?
Series.
Good. Try to compare with this part. Are they same or different? This second one. Is it in series or parallel?
Series.
So now what will you can say about this? Is it in series or parallel?
Series.
This and this is same or different? This one.
Same.
So this combination is series or parallel?
Parallel.
So this must be
Parallel.
good. So K equivalent now becomes 3K plus 3K, that is 6K. Time period equals to 2 pi root under m by k. We have mass of m as 2 and k equivalent as 6k. So on solving, you'll get 2 pi root under m by 3k. Nabila, is it clear?
Yes, sir.
Mazia, any doubt?
No, sir.
Okay. Nabila, done?
Yes, sir.
Okay, so this is all about combination of string. Next, we have to define oscillation on the basis of medium of surrounding. So mainly we have two different types of oscillation. One is undamped oscillation and the other one is damped oscillation. Suppose a spring attached with bob is freely oscillating without any non-viscous medium. So in this part, its amplitude will be constant. But suppose if there is some viscous medium, like any liquid, air we can say, so this viscous medium will tend to oppose due to its velocity at different point. And due to this opposition, amplitude will gradually decreases exponentially and finally it will come to rest in some time. So this is called damped oscillation, in which amplitude of oscillation continuously decreases. So let me define you various forces acting on this particular part. In first part, if there is no viscous medium or viscous force, so amplitude of oscillation will be constant. That is called undamped oscillation. But in second part, if there is some viscous medium, then it will experience some viscous force during its motion, which will tend to decrease its amplitude. So if there is viscous medium, so amplitude of oscillating particle will decrease exponentially. That is called damped oscillation. Gautam, is it clear?
Yes, sir.
So in first part, force acting on particle will be with spring force due to its elongation. So force acting will be just minus of kx. So if you solve this part, you will get y equals to some a times sine omega t, where a is constant amplitude. But in second part, net force acting on body will be viscous force as well as spring force. So for viscous force, I had defined you in fluid F equals to 6 pi eta r times b, where 6 pi eta r is called b, that is damping constant, multiplied by v. And since this force is opposing in nature, so there will be some negative sign. So first viscous force and second spring force. So if you simplify this part, you will get amplitude equals to a naught times e to the power minus b over 2m into t. Expression of amplitude like this, in which a naught is maximum amplitude at time equals to 0. On further increasing time, it gets exponentially decreases. So this is called damped oscillation. If I plot graph related to this part, since the amplitude of oscillating body is constant, so maximum and minimum amplitude will remain same, like this. But in second part, since amplitude is decreasing exponentially, so graph will be like this. And finally, it will come to rest after some time. Krishna, any doubt?
So can you explain why we are considering it as negative 6V?
Viscous force is opposing nature. That's why force will be opposing its motion. Hence it is negative in sign.
So why V, sir?
I define you this particular viscous force according to Stokes' law. Let me just show you just 1 minute. This is Stokes' law. And here I define you. F equals to 6 pi eta r B, where 6 pi eta r is called B, that is damping factor. So force will be equals to minus of B times V. Okay.
Okay, sir.
Raza, any doubt? Okay,
Sir?
let's write it down. Yes.
I did not get this formula with the exponent.
Okay, okay. Just write it down. I'm deriving this part.
So what is E?
Exponential function. Have you all done?
Just a minute, sir. Done, sir.
Nabila, done?
Yes, sir.
Okay. Now related to this above part, as we had F equals to minus of B times V minus of K into Y, we may write force is equals to mass times acceleration minus of B times V minus of K times Y. Now move this mass to right side. So you'll get A equals to B by M times velocity, K by M times Y. Now acceleration is second derivative of displacement with respect to time. If you move this term to left side, you'll get B divided by M times velocity, which is dy over dt, and plus K by M times Y equals to 0. So this will be your general differential equation related to this part. Now, if you solve this expression, you will get y equals to a naught e to the power minus b over 2 times of m into t multiplied by cos omega dash t plus phi. So expression related to damp oscillation will be like this. Now, this will be amplitude, which is exponentially decreasing. Gautam, is it clear?
Yes, sir. What is the omega dash?
Omega dash, it's new angular velocity in this part.
Since the angular velocity is also changing, that's why.
Yeah.
Oh.
So omega dash related to this part will be somewhat like k by m plus b square by m and so on. We don't have to apply these different terms. Just remember the amplitude part. You'll get amplitude like this, which is exponentially decreasing. That's why it is called damped oscillation.
Will there be questions on the this equation?
No, they will ask you only the definition part.
Okay.
You will have to solve these different equations in next year in class 12. And since you have only bio, okay, you're not a math student.
Okay, so we don't have to solve this equation?
Yeah.
Oh, okay.
So any doubt up to this part?
Sir, is that minus b by 2m the exponential power of e?
Yeah.
Okay.
B is damping constant and 2m t is the exponential power of that exponential function. On the value of t, it getting exponentially decreasing.
Okay, sir.
Also, numericals won't come from this part.
No, there will be no numerical related to this part. Have you all done to this part?
Yes, sir.
Okay, so this is all about the entire part of simple harmonic motion. We have just finished it. In next class, we'll start new chapter, that is waves. Okay.
Okay, sir.
Okay, sir.
Okay then. Thank you.
Thank you, sir.
Thank you, sir.